Hello. In the last lecture, we had started talking about microwave amplifier. So, we will continue. We started with the simple inverting amplifier using op-amp. Then I mentioned about the transistor BFP 520. Then I had mentioned about the transistor S parameters for given biasing conditions, and we had seen that S21 decreases as frequency increases. And this is the plot for the S11. We had also noticed that S11 has a non-zero value over the frequency band. Hence, it is important to design impedance matching network in the input side as well as at the output side. Hence, we looked at the derivation for gamma in of the device, which is given by this particular expression over here. Then we looked at the derivation of gamma out of the device, which is given by this particular expression here. After that, we use Mason's signal flow rule to find out the gain of the amplifier, where the objective was to find B2 divided by Bs, and we had used this signal flow and then applied the Mason signal flow transfer function formula, and after that we calculated path from point Bs to B2, and then we found out what are the different loops, and then we found out overall B2 by Bs. After that, we looked at three different gain expressions: operating power gain, then transducer power gain. Then we talked about available power gain, and this happens when both gamma in is equal to gamma s conjugate and gamma L equal to gamma out conjugate. After that, we looked at the expression for transducer power gain, and we had seen this particular expression over here. So, this is the point where we left in the last lecture. Let us continue from here now. So, as I mentioned, this term corresponds to the input side, which can be maximized by using proper input impedance matching network. This is the gain because of the device S21, and this term can be optimized by properly designing output matching network. Even though, as I mentioned earlier, this is this input side, but gamma in depends upon gamma L. So, somehow dependence of output is coming over here. Similarly, in this particular expression, you can see there is a gamma out here, but gamma out depends upon gamma s. So, this output really speaking depends on again the input side. So, to make things simple, we are going to take a few cases. So, let us take these cases one by one. So, the first case which we are going to take is a case 1, matched transducer power gain. What this really means, that if gamma s is equal to 0 and gamma L is equal to 0, then the previous expression reduces to this particular term only over here. So, this is kind of obvious because that is how S parameters of the device is measured, because what you do to measure S parameter, we terminate the output and the input side with 50 ohm. Okay. So, if it is 50 ohm, then gamma S will be equal to 0, gamma L will be equal to 0. So, this is the matched gain. Now, let us take a special case of unilateral transducer power gain. This is defined when S12 is equal to 0. That means power flow is only in one direction, and in the other direction there is a no power flow. That is why it is known as unilateral case. In case of bilateral, power flow will be in both the direction. So, when S12 is equal to 0, you can see here that there is a no gamma in or gamma out term right now, because gamma in is now equal to S11 and gamma out is equal to S22 when S12 is equal to 0. Now, from GTU we can find out what is the maximum unilateral transducer power gain, which is defined by GTU max, and this situation will happen when gamma S is equal to S11 conjugate. Please remember here, gamma S should have been gamma in conjugate, but gamma in is now equal to S11. Gamma L should be equal to gamma out conjugate, but because S12 is equal to 0, gamma out is equal to S22, hence gamma L is S22 conjugate. Now, we substitute this value over here. So, then this expression simplifies to this particular expression here. Let us see how. Gamma S is equal to S11 conjugate. So, magnitude of that will be S11 square. Over here this is S11, gamma S is S11 conjugate. So, S11 multiplied by S11 conjugate will become S11 square. So, you can see that there is a 1 minus S11 square here, this one here is 1 minus S11 square and whole square of that. So, one of these terms will get cancelled. So, we are left with 1 over 1 minus S11 square. Similarly, this term simplifies over here. Now, you can see interesting thing over here, GTM is equal to S21 square when gamma S is 0, gamma L is 0. But let us see now what this expression gives us. S21 square is there as it is, but now if S11 is not equal to 0, let us assume say S11 is equal to 0.5, then what will happen? S11 0.5 square of that will be 0.25, 1 minus 0.25 is 0.75, this term will be now equal to 4 by 3. So, that means gain can be increased by a factor of 1.33 if we do proper impedance matching. Let us look at this over here. Let us take another example. Suppose S22 is 0.6. So, 0.6 square will be 0.36. So, 1 minus 0.36 will be equal to 0.64. So, 1 divided by 0.64, you can say this factor will multiply the whole gain by approximately 1.6 times. So, one can get much larger gain by properly designing impedance matching network at both input side as well as the output side. However, at microwave frequency, whenever you want to design an amplifier, it is very important that you check the stability of the amplifier. So, let us see how we define stability of an amplifier. Let us take a unilateral case. Now, in this situation S12 is equal to 0, that is how unilateral is defined, that signal is only going in one direction, there is no signal going in the opposite direction, that means S12 is equal to 0, and if there is no feedback going to the input side, this particular thing will remain always stable, that means it is unconditionally stable. And in this particular case now gamma in will be equal to S11, you can just substitute S12 equal to 0, and gamma out will be equal to S22. So, it will always remain stable if it is a unilateral case. Now, for bilateral case S12 is not equal to 0, then we have to check stability of the amplifier. So, to check the stability of the amplifier, we need to do two things. One is we have to see what is the stability factor K value. So, K is given by this particular expression. Later on I will tell you how to derive this particular expression. So, right now let us take this as it is. So, what are the conditions for the amplifier to be stable? First thing is delta should be less than 1. What is delta? It is determinant of S matrix S11, S22 minus S12, S21. And when delta is less than 1 and K is greater than 1, then amplifier is unconditionally stable. So, what will happen if delta is greater than 1? I just want to tell you, for majority of the devices delta will not be greater than 1. Okay? For majority of the devices delta is in general less than 1. Okay? But however, if delta is greater than 1, in that particular situation K should be less than 1. So, please remember, if delta is less than 1, then K should be greater than 1. If delta is greater than 1, then K should be less than 1 for the amplifier to be unconditionally stable. Now, let us look at now the derivation of stability circles. It will be obvious by the next slide what do I mean by stability circles. Okay. So, let us look at the condition. For unconditional stability, gamma out should be less than or equal to 1. You have to actually think about a Smith chart. Smith chart represents gamma equal to one circle, and within that circle it actually represents all the real value of the impedance to be positive imaginary part can be positive or negative. But what if the real part of the impedance is negative? In that particular situation, gamma out will be greater than 1. We can just take a quick example here. Just imagine now, let us take an example of Z out is equal to minus 10. Then what is the expression for gamma out? This is equal to Z out minus Z0 divided by Z out plus Z0. If we take Z out as minus 10, then gamma out will be minus 10 minus 50, which will be minus 60, divided by minus 10 plus 50, which will be plus 40. So, minus 60 by 40 will be minus 1.5. In that particular case, gamma out magnitude is greater than 1. For all positive value of real impedances, gamma out will always be less than or equal to 1. In that particular case, we say it is unconditionally stable for all values of the load impedances. So, let us start with an expression for gamma out. So, this is the expression for gamma out. We put the limiting case when this is equal to 1, and now substituting the value of gamma out over here. So, this is the term. Now, we have to simplify this particular term over here. So, let us see now the numerator part S22 minus delta gamma S. Since we have magnitude of that, it is a complex number. So, that is to be multiplied by its complex conjugate. The denominator goes over here, so which is right over here. So, now we have to multiply these terms. So, S22 multiplied by this term here. So, you can see that this is complex conjugate. So, that term will come here. So, that complex conjugate will come over here. It will become S22 conjugate minus delta conjugate and gamma S conjugate. So, now we have to multiply these two. So, S22 into S22 conjugate will be S22 square, then minus S22, then delta star gamma S star. Then from here minus delta gamma S S22 star, or you can say S22 conjugate, and this multiplied by this will be delta square gamma S square. Similarly, we can write the right hand side. So, this will be 1 minus S11 gamma S, then minus S11 star gamma S star, because this will come inside, and then magnitude term corresponding to the product of these two terms. So, now what we have done over here, we have separated out the gamma S terms. So, gamma S square, the corresponding coefficient is given here, then gamma S term, which you can see from here, put things together, then gamma S conjugate terms, and then whatever is left out. So, now this particular thing can be represented in the form of the circle. So, let us see what is the form of the circle. So, this is the equation of a circle in the polar coordinate. You might be familiar with the equation of circle as x square plus y square is equal to a square. That is in rectangular coordinate, or we say Cartesian coordinate. This is the equation in the polar coordinate. So, what is this equation here? Let us see. Gamma S is the source reflection coefficient. This is the center of the stability circle, and this is the radius of the stability circle. So, let us expand this term. So, this would be gamma S minus Cs multiplied by its conjugate value. Rs is a real value because radius has to be a real value. So, that remains as it is. Now, we open this particular thing. So, we have gamma S square minus the other terms are obtained multiplying these terms. So, gamma S Cs conjugate minus Cs gamma S conjugate plus Cs square, which is equal to Rs square. So, now from the previous equation, dividing that by this particular term, we can write equation 1 in this particular form. Now, comparing equation 2 and 3, let us see what we have. So, gamma S square is there as it is. This is gamma S Cs conjugate. So, this would be Cs conjugate. This is minus Cs gamma S conjugate. So, this term will be Cs. So, Cs is given by this particular expression over here. Now, how to find the value of Rs? So, this is the one term which does not contain gamma S. So, corresponding to this here, you can see that this will be now Cs square minus Rs square. So, now we already know what is the expression for Cs. So, substituting the value of Cs over here and simplifying for Rs, we can get the expression for the radius of the stability circle. In the similar fashion, one can find out the center and radius of the stability circle for the load. So, equation of a circle for load would be in a very similar fashion, gamma L minus CL square is equal to RL square, and by using the symmetry we can find out the expression for CL and RL. So, let us take an example so that you understand how to calculate these different stability circles and how these are represented on the Smith chart. So, this is an example. S parameters of a transistor at 800 megahertz are given. So, these are the S parameters. So, we want to find out what is the stability of the transistor and plot stability circles on Smith chart. So, for the given values of S parameters, what we need to do? We need to find the value of delta and K. So, delta is given by this particular expression. All these S parameter values are given. So, we can substitute these values of S parameters and then do complex calculation. This is the value which is obtained for delta. We can see that the magnitude of delta is less than 1. Now, let us find out the value of K. In the expression of K, there are no complex numbers, all are magnitudes. So, the calculation is relatively simple. So, we substitute these values and find out that K is equal to 0.547. That means it is not greater than 1. Hence, this particular transistor is not unconditionally stable. But instead of saying amplifier is unstable, we generally use a little different term. We call it transistor is conditionally stable. What it really means is that for certain cases, this particular transistor may be stable, and if you satisfy those conditions, then this transistor can be used as an amplifier. But when I discuss about the oscillator, the same thing I am going to say that this particular transistor is unstable. So, please do not mix up. Here, since we are designing this transistor as an amplifier, we want amplifier to be stable. So, we are going to find out what are those conditions, for which conditions the transistor is stable. And for oscillator design, we will actually see for which condition transistor is unstable, and then we will use the unstable region to design oscillator. This will be more clear from the plot of the stability circles. So, by using the expression of Cs and Rs, we can calculate the values of Cs and Rs for given values of S parameters. So, this is the value of Cs and this is the value of Rs, and corresponding to the output stability circle, these are the values of Cl and Rl. You can actually see over here that Cs is now equal to 1.79. 1.79 will not be within the Smith chart. Please remember that Smith chart only represents gamma less than or equal to 1. Here this is the center and radius of the gamma S, which is input stability circle. So, how do we locate that? So, what you need to do, you measure this particular distance here, call this particular thing as 1. So, now we need 1.7. So, let us assume that this particular distance is 10 centimeter. So, if this is 10 centimeter, then 1.79 will be equal to 17.9 centimeter. So, you draw this particular line at an angle of 122 degree. So, this will be angle 122 degree. So, this will locate the center Cs. Now, you can see Rs is equal to 1.04. So, since we have assumed this to be 10 centimeter, this will be equal to now 10.4 centimeter. So, with the radius of 10.4, you draw this particular circle. On paper, you may not be able to draw the circle as it is going out of the Smith chart. What you can actually do is just calculate the difference of this number here. So, 1.79 minus 1.04, which is equal to 0.75. So, again assuming if this is 10 centimeter, 0.75 will be 7.5 centimeters. So, locate this particular point here, okay, and then approximately draw this particular arc. So, even if you can't draw, it is okay. Now, let us just look at the output stability circle. So, we have to locate the center. So, again this one here is at an angle of 48 degree. So, draw a line at an angle of 48 degree, then 1.3 minus 0.45. If you see the difference of this particular thing, the difference is about 0.85. So, if this is 1, note down what will be 0.85, locate this particular point and approximately draw this particular arc or circle. Now, this is the unstable region for gamma S, this is the unstable region for gamma L. So, you need to avoid this particular region over here. So, do not choose the value of gamma S in this particular region, do not choose the value of gamma L in this particular region here. So, if you choose the values of gamma S and gamma L in this particular region, then amplifier will become unstable. However, when we want to design oscillator, we have to choose the values of gamma S in this particular region and for gamma L in this particular region. So, just to introduce the concept of the oscillator. So, what do we generally do for oscillator? We choose a point in this particular region which is most unstable region. So, let me just ask you a question, you can think about it. So, let us say point A, point B, point C, point D. Which is the most unstable point among A, B, C, D? So, the actual answer is D, because this is deep inside the unstable region here. You can actually say that okay, well, A is also unstable, B is also unstable, C is also unstable. Why we do not take these points? The reason for that is because of external factors. The biasing condition may change, the external components which you have used, that they may have a tolerance value, and also many of these devices parameter also may change from batch to batch and lot to lot. So, it is always better for design of the oscillator, you take a point which is most unstable. This will be more clear when I discuss about the oscillator design. But for amplifier, please avoid this particular region and take gamma S value which is as far as possible. Similarly, for gamma L, take the values as far from this particular place over here. Now, we are going to look at constant gain circles. So, we will first start with the unilateral case. So, for unilateral case, we had seen that this is the expression for GTU and this is the expression for GTU max. Generally speaking, it will be specified that we have to design an amplifier for a given gain. So, let us say for the desired GTU gain, what we do? We choose the value of GS and GL. Why we separately choose? Because this represents the input side, this represents the output side. So, we can design impedance matching network for input side as well as the output side separately. But before you proceed for this, first of all, you must find out what is GS max and GL max and what is the total GTU max. So, the desired GTU gain has to be less than GTU max. Suppose if GTU max is 12 dB and if the problem says you have to design for a gain of 13 dB, well, that is not at all possible. So, it is important to calculate the value of GTU max. Okay. So, now for desired gain, once you know that maximum gain is more than the desired gain, choose the value of GS and GL. So, the next step is you find out the normalized GS which is GNS, this will be equal to GS divided by GS max. Similarly, GNL will be GL divided by GL max. So, in this expression, let us substitute the value of GS max. So, we actually can find out GNS equal to GS. Since GS max is 1 divided by this term here, that will go in the numerator. So, now GNS is equal to this particular term which is coming from here and this term corresponds to the GS max term. In this expression, the only unknown is gamma S. Other values are known, S11 is known and GNS is known. So, we solve this particular equation for gamma S, and that will lead to the constant gain circle. So, solving for gamma S in the form of gamma S minus CGS square is equal to RGS square. By solving the previous equation, we get CGS and RGS expression. Similarly, for load, we get expressions for CGL and RGL. So, these are the expressions for center and radius of constant gain for source. These are the expressions for center and radius of constant gain circle for load. Let us just look at the special case. For maximum gain, GNS is equal to 1, that means normalized value is equal to 1, and if we put GNS equal to 1 here, let us see what we get. So, CGS will be equal to 1 over here, and this term is 1 minus 1. So, that will become 0. So, this term becomes 0. So, CGS becomes equal to S11 conjugate. Let us see what happens to RGS. So, when GS is equal to 1, so this becomes 1 minus 1. So, that term will be 0. This will be 1 minus 1, this term is 0, but the denominator will be 1 minus 0. So, this particular thing becomes equal to 0. This is kind of obvious that for maximum gain, we know that the gamma S should be equal to S11 conjugate, and that will be a single point. So, for maximum gain, this expression reduces to this simple form, whereas for other values of GNS, we have to calculate CGS and RGS. In the same way, one can derive the expression for the load side. So, these are the expressions for the center and radius of the constant gain circle for load. In the next lecture, we will see what happens if S12 is not equal to 0, what kind of a error is obtained if S12 is not equal to 0, and then we will take a complete example of an amplifier design. So, thank you very much. See you next time. Bye.